WTW 124 2021 exam. Okay, so let's look at the first question. Suppose x, y, z are real numbers such that this um, cross product is equal to x, y, z. Determine x plus y plus z. So for that we first need to do the cross product between these two vectors. Just a recap, a cross product of two vectors will produce a vector. Okay, so let's go do that. Produce a vector. First of all, 3 times 5 minus 2 times 1, and then 1 times 1 minus 2 times 5, and then the last component will be 2 times 2 minus 1 times 3. Perfect. So now this vector will be equal to 13 minus 9 and 1. Okay, so if we add these up, just like they ask, it's 13 minus 9 plus 1. So this will be 4 plus 1, which is 5. So B is the correct answer. Our next question, let A be a real n by n matrix, which of the following statements are necessarily true? So if A is not invertible, we know that the determinant, there is no determinant, and if there's no determinant, there will be no solution. So if it's not invertible, it has no solution. So let's continue reading. Then for every B, for element in Rn, AXB has infinitely many solutions. This does not seem right, because if it doesn't have any determinant, because it's not invertible, it will have no solution, not infinitely many solutions. So this is wrong. So if AXB has no solution, remember, if it has no solution, it has no determinant. If it has no determinant, it means it is not invertible. Let's go read further. For some B in element of Rn, then A is not invertible. This is indeed correct. Not invertible, no solution. So these two test the same concept. And then A squared is invertible if and only if A3 is invertible. So this is true. If A3 is invertible, it must mean that A2 is also invertible. So I would say II and III is correct. So that is C. Okay, next question. Determine this. So I see x and e to the power 2x. So two bases. Okay, and this x can basically be taken away if we use integration by parts. So let's go do it. Let f of x be equal to x and g dash x be equal to e to the power 2x. So f dash x will be equal to 1 and g of x will be equal to a half e to the power 2x. So we integrate to get this part. And remember to divide by this 2, this differentiator. Cool. So now we have this, and now we can basically rewrite this integral as the following. So x times a half e to the power 2x integrated from 0 to 1 minus the integral from 0 to 1 of a half e to the power 2x dx. So now in the integral we don't have any x left, we only have the e part, so that's perfect. So if we substitute in the 1 here, we will get a half e to the power 2 minus, if we substitute the 0 in here, which is just 0. And then subtract this integral. So this integral will be a quarter e to the power 2x between 0 and 1. So if we substitute in this 1 in here, and remember to multiply in the minus, we will get minus 1 over 4 e to the 2. And then if we substitute the 0 in here, and remember to multiply in the minus, it'll become minus a quarter. So it'll be adding a quarter. Okay. And then if we simplify even further, we'll get a quarter e to the 2 plus 1 over 4. So the answer will be D. Perfect. Now number 4, we have a limit, but if we just substitute in this 1 in here, we'll get a 0 at the bottom. So this gives us a clue we're going to use L'Hopital's rule. Okay, so let's go differentiate the top part and differentiate the bottom part. Now let's go do the top one first because that's a integral. And we want to differentiate this integral. Okay, so we know now that this inside function in the integral is just a function of t. It describes something with t. Okay, so we know now that the integral can just be represented as f of x, well f of t actually, between 2x and 2. Don't make that mistake. Between 2 and 2x. Okay, so if we do that, we will get f at 2x minus f at 2. And if we differentiate this, it will be this differentiated, which will give us f of 2x. But remember, by product rule, we should also multiply it by this differentiator, what's inside of the function. So 2 minus, this is just a constant, so it will be minus 0. So that's exactly what we're going to replace in here for this. So the limit where x goes to 1, remember now we already differentiated at the top, so the top will be 2 times that function, but instead of a t we have a 2x. It will be 2 times 1 plus 2x cubed over this differentiated, which will give us 3x squared. Okay, so if we simplify this, we will get 1 plus 8x cubed over 3x squared. And if we substitute in our 1 to this limit, now it will actually work because this bottom is not 0. Then we'll get 2 times square root of 9 over 3. It's just 2 times 3 over 3, and this is just 2. So our answer will be A. Perfect. Now number 5. Determine all real values p for which this converges. Okay, so let's go rewrite this as a limit to make it easier to work with. Okay, x 7 minus 2p dx. Let's go quickly do this integral. So this will just be 1 over 7 minus 2p plus 1. Okay, 7 minus 2p plus 1. Perfect. Remember, I add 1 because that's how integration works. You divide the front part by the exponent plus 1, and then you add 1 to the exponent. Perfect. So this will be evaluated between t and 1. So the limit where t goes to infinity is equal to 1 over 8 minus 2p x to the power 8 minus 2p, still evaluated over that interval. Let's go substitute all of these values inwards. It will be 1 over 8 minus 2p, and then t to the power 8 minus 2p minus 1 over 8 minus 2p. Okay, so now remember, an integral converges when we can use a p-test. I see something that can be a p-test. So for instance, 1 over x squared. By the p-test, this converges because if we look at just x squared, it's a parabola. So this area will just go on to infinity forever and ever. But if we say this, or even just this, it will look something like this. It's something that converges to a number. It gets closer and closer to actual value. So by the p-test, if this is negative, if this part can be proven as negative, then this converges. So 8 minus 2p should be less than 0, because then this, by the p-test, converges. Okay, so 8 will be less than 2p. So 4 will be less than p. And it's that one. It's b. Okay. And now 6. Let f of x be equal to this. Suppose this is the second Taylor polynomial for this, about x is equal to 1. Perfect. And we need to determine c. Remember, this is the second derivative part. So this c will be the second derivative at 1 over 2 factorial. That's what c will be equal to. Okay. C will be equal to this. So let's quickly go get the first factorial of this. Okay. That is something quite easy to calculate. It's just 1 over x squared plus 2 times the differentiable of the inside function, which is just 2x. Okay, and now to get the second derivative, we need to use the chain rule with these two. So this differentiated will be minus 2x x squared plus 2 to the power minus 2 times 2x plus 1 over x squared plus 2 times 2. Perfect. But we need this evaluated at x is equal to 1. So if we substitute 1 into this, it will become minus 2 times 2 over 9 plus 2 over 3, which is just minus 4 over 9 plus 2 over 3, which is just minus 4 over 9 plus 6 over 9, which is 2 over 9. Remember, this is this part. So that's what we got here. So we now know that the second differentiate at 1 is 2 over 9. And if we divide this by 2, we'll get 1 over 9. So the answer is just D, 1 over 9. Question 7. Consider the curve with parameterization Rx this. Okay, so now find the point on the curve where the tangent line is vertical. So if the tangent line is vertical, it's going to look something like this. So this is where the differentiate of the x component will be 0. So where this, the x component, will be equal to 0. So the x component differentiated is just 2t minus 4. And we need that equal to 0. So if we calculate t, we'll get t is equal to 2. So now let's go work out what this is at t equals to 2. It will just be 4 minus 8, and then 8 plus 3. And this is minus 4, 11. So our answer will be A. Last question for multiple choice. Let Z be a complex number. Which of the following statements are necessarily true? Okay, so A is a bit controversial because according to me, this should be correct, but according to the memo, it's not correct. I'm going to show you why I say it's correct. So if you say Z squared, so A plus BI squared, and we take the modulus of that, it would be the modulus of A squared plus 2ABI minus B squared. Okay, and this will just be A squared minus B squared plus 2ABI. And if we take the modulus of this, it would be the real part squared plus with the imaginary part squared. And this will just be a to the 4 minus 2a squared b squared plus b to the 4. And then this is also plus 4a squared b squared. So remember, this is for I. Okay, and this is a to the power 4 plus b to the power 4 plus 2a squared b squared. And if we factorize this, it will be a squared b squared, a squared b squared plus plus. So basically we'll only have one of these left. So a squared plus b squared. So that's for that side. And then just for the modulus of a plus bi, it would be square root of a squared plus b squared. So this, to me, it seems like it will always be greater or equal to this. So according to me, this should be correct. Okay. Okay, so this should be correct. And then let's test II. Okay, II says the imaginary part of z squared is equal to 2 times the real part of z times the imaginary part of z. Okay, so again, z squared is equal to what? Is equal to a plus bi squared. This is equal to a squared plus 2abi minus b squared. Okay, so they tell us that the imaginary part of z squared, so this part, 2ab, should be equal to 2 times the real part of z. So 2 times the real part of z times the imaginary part of z is just equal to 2. What is the real part of z? The real part of z is just a, and the imaginary part of z is just b. So this is also correct. Perfect. So now for our next part, for number 3, they say that z minus the conjugate of z is a real number. So let's go test that theory. So a plus bi minus a minus bi will give us a plus bi minus a plus bi. This will give us 2bi. So this is an imaginary part, and they say it's a real number. So this is false. This doesn't work. But now for number 4, they tell us that we have this curve or something, and they tell us this is a line in an argon plane. So let's go test that theory. So this is IV. So if we take the modulus of z minus 3i, okay, let's just say is a plus bi minus 3i, then this is a plus b minus 3i. I. And if we take the modulus of that, it will just be a squared um, plus b minus 3 squared. And on the right hand side, we have z minus 2. So this is equal to a plus bi minus 2, and the real part is a minus 2 plus bi. And then this modulus will just be a minus 2 squared plus with b squared. Let's simplify both of these sides. So this would just be a squared plus b squared minus 6b plus 9. And this is a squared minus 4a plus 4 plus b squared. Remember, these two are equal to each other. So if we square both of them to get rid of their square roots, be a squared plus b squared minus 6b plus 9 is equal to a squared minus 4a plus 4 plus b squared. So now we know that these two will cancel each other, these two will cancel each other, and what we'll have left is something in this format. So if we can simplify this, let's say minus 6b, take this over, and it will be plus 5 is equal to minus 4. And if we divide by minus 4, we'll get minus 3 over 2b minus 5 over 4 is equal to a. And this is actually the formula of a straight line. Okay, so I say these 3 are correct, but according to the memo, only 2 and 4 are correct. Okay, now section B, question 9. Use Gauss elimination to solve the following system of equations. Only use one row operation at a time. When in row echelon form, write down the system of equations corresponding to the final augmented matrix, and then use backward substitution. So first of all, let's write this as a matrix form. It'll be 1, 2, 0, 1, 1, 1, and then 2, 1, 2, augmented with 8, 9, 5. Okay, so our first row operation will be to cancel out this to get this as a 0. So we're going to change row 2 to row 2 minus 2 times row 1. Okay, so row 1 and row 3 doesn't change at all. 2, 2, 8, and 5. The only thing that changes is row 2. So 2 minus 2 is 0, 1 minus 2 is minus 1, and then 1 minus 4 is minus 3. And 9 minus 16 is minus 7. Perfect. And then the next thing, we need to get this as a 0. So row 3 will become row 3 plus row 1. So row 1 and number 2 stays exactly the same. 8 minus 7. 0 plus 0 is 0. 1 minus 1 is 0. And then 2 minus 3 is minus 1. And then 5 minus 7 is minus 2. So our new system of equations will be x plus y plus 2 times z will give us 8. This is row 1. And then minus y minus 3z will give us minus 7. This is row 2. And minus z is equal to minus 2. This is row 3. So now, using backward substitution, we start at row 3. So minus z is equal to minus 2. So that just means z is equal to 2. And now row 2, because it's backward substitution. So minus y minus 3 times 2 is equal to minus 7. So minus y is equal to minus 7 plus 6. So y is equal to 1. And then last row, our 3 is x plus 1 plus 4 is equal to 8. So x is 8 minus 4, which is 4, minus 1 is 3. So our proposed solution will look something like this. xyz is equal to 3, 1, 2. So let's go test our proposed solution. Is 3 plus 1 plus 4 equal to 8? Yes, it is indeed. Is 6 plus 1 plus 2 equal to 9? Yes, it is. Is 1 plus 4 equal to 5? Yes. So our solution will indeed be xyz is equal to 3, 1, 2. For our next question, give a geometric interpretation of the system above and their solutions. So these are two different planes. So we have 3 planes and we have a particular unique solution. So that just means these 3 planes come together at that one single point. So this represents 3 planes that intersect at a unique point x 312 such that x is an element of all planes. Cool. So it just means these planes intersect at this point. Perfect. So now question 10. Determine I if we have this. So first of all, let's go factorize the bottom. Then we'll have x 1 minus 3x dx. So this gives me a clue that we're going to use partial fractions first. So for some a, b is an element of R, we have a over x plus b over 1 minus 3x will be equal to 1 over x 1 minus 3x. So let's go simplify this. This will be a times 1 minus 3x plus b times x over the common denominator. Okay, and if we multiply this out, we'll have a minus 3ax plus bx over the common denominator. Perfect. And now let's group what we have. So a is a constant and there's no other constants. Here's a constant. We have, let's change the sign. Well, let's not change the sign. Let's take out the x. Then we have minus 3a plus b. Okay, this is the x part. Write the common denominator again. 1 over x, 1 minus 3x. So for this to be true, this has to be equal to the other side's constant. So a is equal to 1. And minus 3a plus b should be equal to that side x. And there are no x's on the other side. So this will just be equal to 0. And we already have a is equal to 1. So b will be equal to 3. Perfect. So now we can change this integral to 1 over x plus 3 over 1 minus 3x. Everything here, dx. So we can actually split this up as well, because that's what you can do with integrals, dx. So we know this part, this will just be ln x. Remember to write ln absolute value x. And then there's a test we can do here, okay? The differentiable at the bottom is minus 3. And the top part is just 3. So this answer we can basically take out, and we can write this as a ln of the bottom part. Remember the absolute values. And we add c because this is a indefinite integral. And this will also be our answer. Okay, perfect. So now 10.2 asks us to determine this. So again, I see integration by parts because this is very difficult to solve just by its own. So let's go set a few stuff equal to each other. So let f of x be equal to this arctan function. So arctan 1 over x, okay, and g dash x be equal to 1. So what we do here is we take the inside functions x, which is x to the power negative 1, and then we add 1. Then this will give us x to the power 0, which is just 1. That's why I said it equal to 0. Well, x to the power 0 will give us 1. So you look at the inside functions x, and then you just add 1. So f dash x will give us 1 over 1 plus 1 over x squared. And also remember to derive the inside function because we just derived. We just differentiated. So you also have to differentiate the inside function, which will give us negative x to the power minus 2. Okay. And then if we integrate this to get g of x, we get x. So j is then equal to arctan 1 over x times x minus the integral of 1. Let's make this a minus immediately. So minus 1 over, yes, so this will then be x squared, because this multiplies here at the bottom, because it's a negative exponent at the top, plus, and that will cancel out this one, so it'll just become a 1. And then we times it by this x. Okay, so if we integrate that part, just simplify it quickly. We can take out this minus to the front. Then will be x over x squared plus 1. Again, let's differentiate the bottom part. Then we get 2x. And the top part is x. So we'll have a half. And that is actually the ln rule. So we add a half of ln x squared plus 1. Remember to add plus c. Okay, cool. But now here we can actually just write it as curly brackets or round brackets, because I'm going to write that reason with that. It's a half ln x squared plus 1 plus c, since x squared plus 1 is greater than 1 for all x is an element of R. And that is also our answer. So arctan 1 over x times x plus a half ln of x squared plus 1. Let's go look at the next question. Question 11. They ask us to show that this transforms into this by using the substitution of x is equal to sine theta. Okay, so now let's go do it. Let's go change this integral. So x squared over the square root of 1 minus x squared of dx is equal to this. Remember, x is equal to sine theta. So the top part will now be sine squared theta over the square root of 1 minus sine squared theta. So now this dx part, we can't just write dx because we're changing everything. So now let's go work out what this dx will be. So dx d theta is equal to cos of theta. So it will just change to this, basically. So in the place of this dx, we'll have cos of theta d theta. Perfect. So the top part stays the same. The bottom part, we can change the inside to cos squared theta. Okay, and if we take out that square root, it cancels with the square. Okay, then this cos and that cos cancels out. Then we'll have the integral of sine squared theta d theta, and that is exactly what they wanted. Okay, so now for the next part, 11.2, use 11.1 and determine this integral. Now we need to work out this integral. So we know now that this is equal to sine squared theta d theta because x is equal to sine theta. So now let's actually first go plot that in a triangle, the property they gave us. So they told us x is equal to sine of theta. So if we can stand on theta, this will be x and this will be 1 according to trig. So this will be angle 1 minus x squared. So now let's go try to write this integral in terms of sine or cos or tan or something like that by using properties. So first of all, we know sine squared can be used. We're trying to get rid of the squares. So don't use the formula that says cos squared theta plus sine squared theta is equal to 1. No, we're trying to cancel out the squares. So rather use double angles. So cos 2 theta is equal to 1 minus 2 sine squared theta. Let's use this one rather. So we're trying to get this alone. So it will be cos 2 theta minus 1 is equal to minus 2 sine squared theta. Divide by minus 2, then we'll get a half minus half cos 2 theta. Okay, now let's substitute that into this. So it will be a half minus a half cos 2. So that's what we changed it to. So let's go integrate this rather because it's much easier. So we have the integral of a half d theta minus the integral of a half cos 2 theta d theta. So this will just be a half theta minus. So now remember, if we integrate cos, we'll get a sine, okay? And not negative sign, we'll just get a sine. So this sign doesn't change. And remember, we have to divide this by this inside function differentiated. So it's a half divided by 2 cos of 2 theta. But remember, this cos changes to a sine 2 theta because we just changed it. We just integrated it. Remember to add c. So this will be a half theta minus a quarter of, remember, this we can also change. Sine 2 theta is just 2 sine cos. Perfect. So now basically we just have half theta minus a half sine theta cos theta plus c. And now we can actually work everything out. We know now that this theta part is just arc sin x. So a half of arc sin x minus a half. Now what is sine theta? Sine theta is x over 1. So it's just x. And what is cos of theta? Cos is just this over 1. So it's 1 minus x squared, everything square rooted. So it's half arc sin x minus a half x square root of 1 minus x squared. Remember to add your c at the end. And that is our answer. So now question 12. Let the vector function this be this. So C actually maps out RT. Okay. And D is something different. So prove that C is a subset of D. So we need to prove that this part, this C, is a subset of this entire thing. So this properties of xy, the xy components here, should satisfy this equation, basically. That's what they ask us. Does this component satisfy this conditions? So now, if xy is equal to, well, if xy is an element of C, okay, so that's this one, then xy can be equal to this components. We just use the components. So cos of t plus square root 2 sine of t, and the y component is 2 cos of t minus square root 2 sine of t. Perfect. And we also say this is for t's element of 0 to pi. And now let's see if it satisfies, if these components actually satisfy this conditions. So 2x squared plus y squared will then be equal to what? 2 cos of t plus square root of 2 sine t, everything squared, and then we add the y component squared, sine of t squared. So this will just be cos square t plus 2 square root of 2 sine t cos t plus with 2 sine squared t. Adding with this, so this will be 4 cos square t minus 4 square root of 2 sine t cos t plus 2 sine squared t. Perfect. So now let's multiply the 2. Then we'll get the following. Okay, cos of t plus 4 sine squared t. And then plus the rest that we didn't change in this part. Sine squared t. So now we can see that this part, this plus and this minus will cancel each other out. And now let's group the rest that fits together. So there's 2 cos squared t plus this 2 sine squared t adds with this 4 sine squared t plus 4 cos squared t. Perfect. So now we can take out a 2 here. And then we'll have this left inside the bracket. We can take a 4 out here. Okay. And we know that cos squared plus sine x is just 1. So it's 2 times 1 plus 4 times 1, which is equal to 6. And that is indeed our answer. And that is what we should have gotten. So this component we have is also an element of D. So C is indeed a subset of D because we said that X is an element of C at the beginning. But then we also proved at the end that X is also an element of D because it actually works for both of them. So C is indeed a subset of D. C is a subset of D. So 12.2, let E be parameterized by this. Sketch E, clearly indicate the shape of the curve, all intercepts with the coordinates axis, and give the equations of the two asymptotes. So first of all, we see it's x squared minus something y squared. So because the y squared has the minus in front, we know it will be a parabola in these quadrants. Okay, so somewhere there, that's the general shape it will look. Because y is negative. If y was positive, it would have been there and there. But that's just not the case. So now let's quickly get the x-intercepts. Intercept by making the y 0. So this is what we'll have. So x will be plus and minus 4. So we know these will be minus 4 and 4. Are there any y-intercepts? Let's go see. Y-intercept is where x is 0. So this part will be equal. So y squared will be equal to minus 4. And this just has no real solution. No real solution. So it doesn't have any y intercepts. Perfect. So now let's go start sketching after we have determined the asymptotes. So the asymptotes. So this is kind of cool. So what you can do is basically disregard the 16. Okay, so we just work with this part with the x and the y's. So set it equal to 0. And then we'll get x squared is equal to 4y squared. Let's get the y alone. So it will be a quarter of x squared is equal to y squared. So plus or minus a half x will be our y. So this will be our asymptotes. So let's go quickly draw this sketch. Okay. So this is the x part, this is the y part. And then we know that the asymptotes are these lines. Perfect. And our sketch will be in this quadrant. Draw that a bit neater. Perfect. Perfect. And we know that this will be at 4, 0, and this will be at minus 4, 0. And this is E. It is a hyperbola. Okay, and that is the shape of this function. Cool, let's continue to question 13. Okay, so if we have this curve, if we look at any curve, okay, that's mapped out by RT, okay, and let P be a point basically at A. So here, this point is at RA, okay, be a point on C for some real number A. Write down a vector equation for the tangent line TP to C at P. So we want basically the equation of a tangent line right there. So something to remember. This vector equation will be equal to the point where it's at, plus the directional vector. Okay. So if we look at this directional vector, it will just be the gradient. And we know now that it is the this derived at 8, differentiated at A. Okay. So it will be t directional vector. Remember, directional vector has a t in front or just any real number r differentiated at A. Okay, but they want it in terms of these two. So P is just what? It's RA plus T RA, and this is for T is the element of R. So T can be any value. Remember, it should be able to be there or there or there or there. Anywhere on this line should be a T value because we want the tangent anywhere at T. Okay, so that's why we put this T in front of the directional vector. And that will actually be the tangent line at that point. So 13.2 asks us, suppose RT is this, where T is an element of R. Determine all points of C if this is parallel to the plane with the equation this. Okay, so what this means basically is they want the points where this line will be parallel to this plane. So if we have this plane and it has a normal, okay, then this line should be equal or rather parallel to that normal. Okay. Um, excuse me, if it's parallel to that plane, it should be perpendicular to that normal of the plane. Okay, so let's go get the directional vector of this one. So we already said the directional vector is this. So now let's go substitute that in. The direction of t at that point is r at this, which will just be 3a squared plus 6a, and then the y component will be 2a, and the z component will be 6. Perfect. So now a normal vector for p, so a normal vector for p for the plane basically would just be these numbers, would just be 2, 3, 2. So every number in front of the variable, the unknown, x, y, z, 2, 3, 2. Okay, so we now have the normal vector of the plane. So this plane has a normal vector of that, and we want the directional vector of this. We want all of the values a where this directional vector dot product with this normal vector will be equal to 0 because they need to be perpendicular. Okay, so if we simplify this even further, multiply the first vectors with each other, first components, then we will get 6a squared plus 12a plus 6a plus 12 will be equal to 0. So 6a squared plus 18a plus 12 will be equal to 0. If we divide by 6 everywhere, it will be a squared plus 3a plus 2. And this is easy to factorize. A and a 2 and a 1, a plus and a plus will give us 0. So a is equal to minus 1, or a is equal to minus 2. So now we want all the points where it's parallel to the plane. Okay, so it's parallel to the plane where P is equal to R at minus 1. Okay, which is quite easy to calculate. This will be minus 1 plus 3, which is 2. And then this will be just 1. And then this will be minus 6. Or there's another point at minus 2. So this is minus 8 plus 12, which is just 4. And this is just 4. And this is minus 12. Perfect. Okay, and that's all the points where this determine or P such as this TP. So basically where this tangent line is perpendicular to this plane. Parallel to the plane but perpendicular to its normal vector. Perfect. Okay, so now next question 14.1. Express this in polar form, this with principal argument. Okay, so first of all, to make it a bit easier, let's go quickly draw how this would look, just to help us out a bit. So on this axis, with the real numbers, and this axis will have the imaginary numbers. So the real part is minus 3, and the imaginary part is 3 square root 3. So it will be somewhere there. So we're going to draw our triangle like this. And we're going to set our theta here. And this will be minus 3. And this is just 3 square root 3. So now let's go quickly work out this r. R is just basically the modulus of the z, which will be square root of minus 3 squared plus square 3 square root of 3. With 9 plus 27, which is 36, and the square root of 36 is just 6. So that's our value right there. So a minus 3 plus 3, that entire z will be equal to 6 times cos of theta plus I sine of theta. So let's go quickly check. Cos of theta is minus 3 over 6. So cos of theta is just minus a half. And that will produce plus or minus 2 pi over 3. And sine of theta is equal to 3 square root 3 over 6, which is the square root of 3 over 2. This will produce pi over 3. Just make sure I did this correctly. Sine, perfect, 3, 6. So if we add a half of a pi here, so since this is positive, we will use the positive angle we got here, not the negative angle. So theta is equal to 2 pi over 3. Hence, z is then equal to the r we had, which was 6, times with e to the power I, and then the angle we said we're going to use, so 2 pi over 3, and that's 14.1. Okay, so here they tell us it is given that x is equal to this is a root, okay, of this. Find with reasons all the roots of f of x. So first of all, if they give you a complex root, it is known that the conjugate is also a root, okay? So since 1 plus 2i is a root, the conjugate, well, since this is a root, the conjugate x is equal to 1 minus 2i is also a root. So let's quickly work this out. Let's say x plus this. Okay, remember roots, we take this basically over to this side. So it will be x plus 2i minus 1, and then another root is x minus 2i minus 1. So these are two roots we have for f of x. Let's go quickly simplify these. So x times x is x squared. X times this is minus 2xi. X times this is just minus x. This times x is plus 2xi. This will produce a positive 2. This will produce a negative 2i. This will produce a negative x plus 2i, and then plus 1. So I only see 1x squared. Here is a xi. Here is a xi. So they cancel each other out. Here is a x. Here is a x. They will actually become minus 2x. This one is a minus 2i. This one is a plus 2i. So they cancel each other out. And then this will just be 2 plus 1. I made a small mistake at multiplying out the bracket, so x times x is indeed x squared, and then this will give us minus 2xi, this will give us minus x perfect, and then this will give us plus 2xi. This following part will not give us whatever I had previously, it will give us a positive 4, because it's 2 times 2. And then this is minus 2i, this is minus x, this is plus 2i, and then we have plus 1. So only 1x squared. And then we see here is a minus xi. Here is a plus 2xi. So these two will cancel. Here is a minus 2i. Here is a plus 2i. So these two will cancel. Here we have a minus x minus another x is minus 2x. And then plus 4 plus 1 is plus 5. So this is also, this is a factor of f of x. So we just took these two factors and multiplied with each other. So that's going to be a factor of this. Okay. So the following, we're going to do long division to find out any other factors of this. So let's divide this 2x cubed minus 3x squared plus 8x plus 5. Let's divide it by x squared minus 2x plus 5. So first of all, how many times does this go into this one? It goes in 2x times, and let's multiply this 2x with every single term here. Then we'll get 2x cubed minus 4x squared and plus 10x, and let's minus this. Then we'll get 0. This will become x squared. This will become minus 2x, and then we bring down the 5. How many times does x squared go into x squared? Plus 1 times. And then if we multiply this plus 1 with that polynomial, we'll get x squared minus 2x plus 5. And let's subtract this now. 0, this will be 0, and this will be 0. Perfect. So this is what we have. So f of x is equal to this with what we divided, and then multiply 2x plus 1. So we know that the roots in the start were the following. The roots are the following. 1 plus 2i, 1 minus 2i, and then this one, minus a half. So those are the roots. Okay, so for our next question, question 15. Only 15 and 16 left to answer. So now 15.1 proves that if the absolute value of x is between 0 and 1, then the following must be smaller than 5x. Hint, use the following. Okay. So now let's go quickly manipulate this. Okay. Let's go say x times 3 to the power x plus 2x sine of 1 over x. So let's divide the terms. Let's say this is smaller or equal to x, and then times 3x plus 2x sine 1 over x. Okay, this is the triangle inequality. Triangle inequality. So that's what we used here. So we separated this term from this term. Okay, by using that triangle inequality. So now let's use the stuff that they just gave us. So if this is less than 1, then just what they gave us, then 3 to the power x is between 0 and 3. But if x is not equal to 0, so that means this is not 1 exactly, x is not equal to 0, then the following would apply to the sign part. Because x is not equal to 0, so this sign part, 1 over x, will be less than or equal to 1. So if we go look at the graph for sine, it never goes below -1 and 1, but this is the absolute sign. So it never goes below 0. Okay, 0 excluded. Because x, if x is equal to 0, then this thing will be undefined, this inside of the trig function. Okay. Okay, so now for the following steps, we can just use these facts that we just proved to change this. So we're going to change this part now. But we just say that this will be smaller than 3. This absolute sign will be smaller than 3. So the x we leave the same, but this will be a 3. Okay, and we also just said this will be less than or equal to 1. So this term just basically cancels out. It becomes a 1. So times 1 basically. And then this is equal to what? 3 plus 2 is 5. And that is what we had to prove. Okay, so 15.2. Use 15.1 and prove by definition that this limit where x goes to 0 of this term, okay, that's the previous term we just had, is equal to 0. So we write a proof here. So fix epsilon greater than 0. Okay, just to make sure, x goes to 0, so there's no infinite, and this goes to 0, so there's no infinite. So we can fix epsilon greater than 0, and we should really choose our delta. Okay, so remember, we use two stuff here. Okay, first of all, we said that x is smaller than 1. Okay, then the following holds. So let's choose a minimum for this delta such that it's 1, minimum of 1, or it can actually be epsilon over 5 as well. Epsilon over 5. Okay. So for x is less than delta. Okay, and obviously we know that x is less than or equal to 1 from the previous statement. So x is smaller than 1. That's what we know from the previous statement. Okay, epsilon can be actually equal to 1 as well, but x can't be equal to 1. So by the previous one, 15.1, we can literally say that this inside function to x sine and 1 over x minus 0 is less than 5x. We know this. But we also know that this x is less than delta. So we can actually replace this x with a delta. And we also know that delta is less than or equal to epsilon over 5 from this statement. Okay, so we can actually replace this delta with epsilon over 5. And we know now that this is just an epsilon. And this is true for all epsilon greater than 0. So by definition of a limit, the limit where x goes to 0 in this following function 1 over x is indeed equal to 0. Okay, that wasn't too difficult. So now, question 16. Let z be equal to this, be a non-zero complex number in polar form. Use mathematical induction to prove that this, for all integers greater, where n is greater than 1, you may use the formula this. Okay, so this is quite actually a cool formula to use. So, without proving it. So we need to use mathematical induction to prove this, but we can use this. You may use this formula without proving it. So we need to prove this. Cool. So our basis step is just basically where we prove it for n is equal to 1. So if n is equal to 1, then z to the power 1 z to the power 1 is equal to z, obviously, and that is just r cos theta plus sine, well, I sine theta, because that's for n equals to 1. So that's what we get for n equals 1, and that is indeed true. So now for our induction step, before we do that, let's just write the result holds for n equals to 1, because this is indeed a true statement. Okay. And now let's go make an induction hypothesis. This is just by saying, let's structure this a bit better. Okay, so for k, is equal to 1, and obviously it is greater than 0, assume that z of k is equal to rk, and then cos of k pi plus I sin k pi. Okay, so assume that it actually works. Okay, now we're going to do the induction step. Induction step. So we're going to use this for n is equal to k plus 1. So z to the power k plus 1 is equal to z to the k times z. And we now know that z to the power k is just r to the power k cos of k theta plus I sine of k theta times this r cos of theta plus I sine of theta. Okay, so we use this one that we got here, and we use this first statement we got in the basis step. Okay, and then we'll have r to the power k plus 1 because it's this one and this one. And then we will have cos just remember that we can use this one from here above. So this would just be cos k theta plus that theta plus I sine of k theta plus theta. And we can actually take out a theta here to give us k plus 1 plus I sine theta k plus 1. So the result holds for n equal k plus 1 if it holds for n equals to k for any number. So I'm going to write the conclusion here at the top. Conclusion. Okay. So by the principle of mathematical induction, the result holds for all n is an element of a whole number. Perfect. And that was the entire exam.